Okay, today we are going to learn how to solve for the function of velocity with respect to time using um, some differential equations in calculus. Basically, like what we're going to do is we're going to have an expression where A relates to V, and we're going to learn how to solve um, for V in terms of time. Sounds weird, yes, I know, but today to like give you like a push, because this really doesn't like the easiest problem and the hardest problem, they are kind of like they're not really far apart. Like if you can do the easiest problem, you can also like if you really lock in, you can really do the hardest problem too. So what we're gonna do right now is we're gonna talk about the easiest problem, which will hopefully give you an idea on how to do the hardest problem. So yeah, let's talk about let's talk about probably the easiest problem, and then we'll do the easy problem. So let's first talk about a block moving on a frictionless surface, right? A block moving on a frictionless surface that is subject to a resistive force that is linear to the speed, which basically means that it's moving this way, yes, but there's an opposite force that is acting in the direction against that block. So if you do Newton's second law, where the net force equals the mass times the acceleration, we get that the mass times the acceleration equals the drag force. Okay, now this is pretty good. Now I want you to try and find velocity as a function of time. For example, if we have some initial velocity v naught, so like say this thing is launched at some velocity v naught, how does velocity change with each passing second? So to answer that question, we're going to have to solve this differential equation. And how we're going to do that is first replace A with its definition as dv dt, or the derivative of velocity with respect to time. Now, if you know how to solve differential equations, this is actually really easy. You can do like that. But I'm going to walk you through it as if you don't know how to just solve a differential equation. So here we go. What we're going to do is, in normal calculus, this will probably be easier, but in this one, what we're going to do is we're going to separate variables. So what I'm going to try and do is I'm going to get everything that isn't a v on this side and everything that has a v next to it on this side. So what does that mean? I'm going to divide both sides by v, right? And I'm also going to multiply both sides by dt. And I'm also going to divide both sides by m. What that means, what basically I did is, I got the v's all on one side, the m's, k's, and dt's all on one side. So what I'll be left with is dv over v equals negative k over m dt. Now what you will do is you will integrate. Now the second step, that's your first step, separating the variables. The second step is integrating, but yeah, you integrate with respect to v on one side and respect to t on the other side. But t, we want to make sure we want to integrate from 0 to the given time t, which is just a function. For v, we integrate from v naught all the way to v of t. So that's basically that. And then we end up getting 1 over v of t, which I'll just label as v, minus, natural log, my bad. Natural log of v minus natural log of v naught equals, well, this is just a constant. So this is actually just going to be negative k over m times t, because it's just a constant, plus, because there's a minus, k over m times 0, which is just 0. Okay, so now we got another third step. Second step is done. Third step is solve for v. So what we can do is add this on this side and then exponentiate both sides. So we'd get v of t equals e to the ln of v naught plus negative, no, not plus, it's a minus, my bad, minus k over m times t. And you can simplify this further because you can basically split out the e, and e and ln would cancel. So you would get v naught times e to the negative k over m times t. Sweet. That's what you would get for a simple example. So now we're going to do a slightly more complicated one. Okay, same thing. We have a velocity dependent resistive force, negative kV, on this side, but this time it's not moving horizontal, it's moving vertical. It's specifically downwards. So that is equal to mg. Okay, so same thing. This is a little more complicated now, but it's just the same thing. We're gonna take the net force equation, mg minus kv equals ma. So now we have a, which is basically dv dt, like we did before. Okay, this time a little more complicated this time to separate the variables, but it's doable. We're going to take this entire term and divide it on this side, and take the m and the dt on the other side. So we're going to get dt over m equals dv over mg minus kv. Okay, so first step done. Second step, integrate. So we're going to integrate, same thing as before, t equals 0 to t equals t. V equals v naught to v equals v of t. Okay. Obviously, 1 over m is a constant, so we're gonna do the same thing we did as last time on this side. Remember, 1 over m is a constant, so we're gonna integrate. You get t over m, but you're plugging in a 0 to t, so that's just gonna stay as t over m, which equals, okay, this is, we're going backwards, right? We're going backwards. 1 over something, if you go backwards, that's natural log, right? Because the derivative of natural log of something is 1 over that something. So we're going to have a natural log, right? There's a negative, so we're going to have to do, well, inverse chain rule. We're going to have to divide by negative 1 over k. Yeah. And then we're going to keep the something inside. So mg minus kv. And then we're going to evaluate from v naught to v of t. So put this back up here. T over m. That equals. We're going to evaluate this time. And when we integrate two variables, when we evaluate, we have to subtract the variables. So we get this variable first, so negative ln, you know what, for simplicity's sake, since we're going to have a 1 over k for both sides and a negative, that too, let's multiply the negative 1 over k on, let's multiply both sides by negative k, so the k would actually go on that side, and it clutters up less. So basically all I did was take out the k. The same thing, but the subtraction is still the same. So we're going to have, that's going to equal natural log of mg minus kv, which is basically v of t, but I'm just doing it because it takes up a lot of space. So that's why I'm not doing v of t, but I'm just going to abbreviate it as v. So same thing, again, ln of mg minus kv naught. Same thing. So we're going to add this on that side. We're going to get kt over m, negative kt over m, plus ln of mg minus kv equals ln of mg no, V naught, my bad, mg minus kv. Now, when we e both sides, this is gonna cancel out with the e, because we split the e's, remember, like last time, where we had the ln of v naught minus k over m. We split them and we got the v naught outside. We're gonna do the same thing here. But I'm gonna skip that step. Minus k v naught times e to the negative k t over m equals mg minus kv. Factor mg on both sides and then divide by negative k. So we have mg. This is going to be a little cluttered, so let's multiply the e on on both of these. So we're going to get mg over times e to the negative kt over m minus kv naught times e to the negative kt over m minus mg all over negative k will actually just be v of t.